let's talk about how to describe objects that can speed up and slow down when moving in one dimension. Here you can see a simple number line, and what I'm trying to communicate here is that there's a car at some moment in time t1, and it's traveling at some speed here, and it's going to the right. And then a little bit later in time, at moment t2, it's traveling faster. That's why there's a larger arrow here, and this would be what's called a velocity vector at a particular instant in time. I'm not even giving you the number of the velocity here in terms of its magnitude. I'm just trying to communicate that, hey, look, this thing has sped up. So let's learn how to do this, and I want to build this up through some simple questioning that you really need to pause the video and think about so you can kind of build this concept up from your own thinking. And then we'll kind of wrap it all together with multiple representations. You'll see data tables, graphs, equations, and some simple conceptual reasoning that will all come together to really show you what's going on and how we describe objects that can speed up and slow down. So to begin, let's remind ourselves what's meant by an instantaneous quantity, specifically instantaneous velocity. That's how fast and in what direction an object is traveling at some instant in time or some clock reading, as we've learned to define it. So look at this table over here and maybe pause the video for a second and try to interpret what I'm trying to communicate here about a particular object. Here I have some clock readings, and then I have some corresponding instantaneous velocity values. What is happening here? All right, well, this is pretty easy, and I hope you can see that the object is speeding up. Now, look, we're not looking at position right now. Watch out, because when we first learned physics, we're seeing a lot of variables kind of all at once, and you have to constantly be reminding yourself when we're learning about speeding up and slowing down what you're looking at. And we're looking at velocity here, okay, not position. So this is how fast we're going, and you can see because the units say meters per second. Okay, but let's go further than just kind of realizing that it's speeding up, and let's try to find a pattern in the numbers. Use this helpful sentence frame to see the pattern in the numbers. So go ahead, pause, think, and do some physics here to see if you can extract that pattern. So here's the result. To find the velocity of the object after each 1 second elapses on the clock, it's important that you have that number 1 right there, add 2 meters per second to the previous value for velocity. You can see that here. Every time 1 second elapses on the clock, we add 2 meters per second to get to the next value for velocity. Skip down a few here from seconds 3 to 4. That's 1 second elapses on the clock. And again, we add 2 meters per second to go from 6 meters per second to 8 meters per second. That's the pattern. Every second, we're adding 2 meters per second to update the value of our instantaneous velocity. So now what I'd like you to do is turn this into an equation. See if you can use some abstract symbols. And I'll help you out a little bit here. We want to be able to predict a final velocity value after some amount of time has elapsed. And we also know that we start at some initial velocity value. So see if you can fill in kind of the rest of this equation with information from the problem and build up an algebraic way to produce all of the correct values in the table. So pause, think, and do some physics here. So hopefully you have a formula that looks somewhat like this. However, I've made a deliberate mistake, and I want to see if you can figure out my mistake. So look at the formula, inspect it, and if you're really solid on your ability to think about how units and variables interact together, you might be able to spot my mistake and fix it. So pause the video and see if you can fix my mistake. So we had a problem with the units, and you can see now that I fixed those. Let's double check to make sure they're correct. So if we plug in +2, and the way we'll say this right now is +2 meters per second for every 1 second. I really want you to speak it like that for right now. We'll end up abstracting that to something else a little bit later. But for now, +2 meters per second for every 1 second. Seems like it aligns with what we had down here in our sentence frame. And then multiplied by, I'm just going to pick a clock reading of 3 seconds to test the model. and see if it works. And notice what happens. The seconds here in the clock reading cancel out with the seconds in the denominator there, and we're left with something that makes sense mathematically. We have positive 6 meters per second, plus 0, I won't even write that, but notice how, actually I will, plus 0 meters per second. Notice how we are adding apples to apples, if you will, right? These units match those units when doing addition, and everything looks good. All right, so what would of course happen here? I'm running out of space, but we would have a prediction that says that our velocity, final velocity at clock reading of at a clock reading of 3 seconds would be equal to 6 meters per second. And I'll put a plus sign out there just to be very explicit. And we look in our table and it agrees. So we would test that with another value and it would work, and you would see the pattern here that has occurred. Awesome. So hopefully finding that mathematical pattern was easy for you, and you understand now how the numbers in that data table are interacting with that formula. And we'll come back to that formula and generalize it a little bit later. First, I want to build up some more conceptual understanding. And I have a fact for you to consider. An object changes its velocity by positive 2 meters per second for every 1 second. I'm stating that as a fact for some object. And I have a simple true or false question for you to consider. This object must be speeding up. So based on this fact, answer either true or false. This object must be speeding up. And a quick little note about these types of questions, especially really good conceptual questions, is try to write down what you really actually think. Spend some time doing that. Don't just try to choose true or false to get to the right answer. It feels good to get a right answer. It feels bad to get a wrong answer. But that's really not the point with these great conceptual questions. It's to instead really think about it, make a choice, being okay with being right or wrong, and then getting some feedback on if you were wrong, why, and if you were right, why. And a lot of times you learn more when you're wrong because you really remember those ones. And when you're right, you can learn as well too, which is great. But choose what you really think. Don't try to do some reverse psychology to get the right answer, which I see students doing often when first learning physics. Okay, so take a minute, really think about this one, and we'll see. Go ahead. All right, well, you've thought about it. Let's see the answer. The answer to this question is false. This object must be speeding up, not necessarily true. Now, you might have relied upon the previous example to guide your intuition, and that was great if you did. Nice job there. But there's something else going on here, and I want to kind of share that with you. So to get to our next question, I want to see if you can articulate why this must be false by me providing one more little piece of information. So I've given you a data table again of clock readings every single second, as you can see, and I'm going to write down the first velocity at a clock reading of 0 seconds with the following number. Okay, I would like you to pause the video now, think about what we did in the last segment with our previous data table, and see if you can show why this statement now must be false. Go ahead, pause, think, and do some physics here. All right, hopefully you got it. Notice what I've done. I've taken that previous little knowledge that we talked about in the last segment, I've written it down here. And really this question, I'm asking you to apply this new knowledge to a slightly different scenario to get to that answer of false. So that knowledge was to find the velocity of an object after each 1 second elapses on the clock, add plus 2 meters per second to the previous value for velocity. So let's just do that. Okay, that was the pattern that upheld last time. And if we do that again here, notice what happens. We'll come along and we'll add plus 2 meters per second. It's just addition, okay? And when we do that, watch what happens. Minus 14. Negative 16 plus 2 is minus 14. Do it again. Now add another 2 meters per second. Now what happens? Well, negative 12. Can you continue the pattern, right? Pause the video, continue the entire data table, and then take a step back, reflect on what you've done, and see how that answers our question. Go ahead. All right, so you filled in the rest of the data table, and you should have seen how the numbers are getting closer and closer to 0 as time goes by, because we're adding 2 meters per second every time a second elapses on the clock. So if you were in a car looking at your speedometer, which I've tried to draw over here, it would start at 16 and it would start to get smaller and smaller and smaller, going all the way down to 0. That means we are slowing down. So how fast an object moves, well, that's what we mean when we're talking just about speed. Are we going fast or slow, etc.? And that's the magnitude of the instantaneous velocity. That's just the size of the number without reference to any direction. So this, I know it says minus 16. The minus indicates the direction we're traveling in. So we're moving in the negative direction, but we're going 16 meters per second as our speed. Likewise, a little bit later in time down here, we're still moving in the negative direction because our velocity is negative, but we're moving with 6 meters per second, so our speed is less than it was before, all the way down to 0. And here at 8 seconds, we must be stopped because we're moving at 0 meters per second. All right, great. Now what I'd like you to do is turn this table into a formula. I've given you the initial condition, which says that at a clock reading of 0 seconds, we have an initial velocity of negative 16 meters per second. And I'd like you to construct an equation or a mathematical model that now would work here as well, that would allow you to know at any moment in time the velocity of the object. So go ahead, pause the video, and build that equation. All right, let's take a look. I've rewritten the table here, and we'll plug in our value of plus 2 meters per second for every 1 second. Multiply that by any clock reading at some final moment in time, plus some initial velocity. And in this case, it would be minus 16 meters per second. Now, typically, you won't have a plus and then parentheses and a minus 16 like that. So I'll just erase this and do what we conventionally do here, which is just minus 16 meters per second. And there's our model. We could apply it, see if it works. So when we have a final clock reading of 4 seconds, let's see if it works. So we plug in and we'd get plus 2 meters per second for every 1 second, multiplied by 4 seconds of time, minus off our initial velocity of 16 meters per second, do some unit cancellations, and keep going through the math, and we'd get plus 8 meters per second, minus 16 meters per second. And that's going to give us exactly what our instantaneous velocity is here at 4 seconds in time. You don't have to put that at 4 seconds, but I just put that down there just to communicate that at that exact instant or clock reading, here is exactly how fast we're traveling. And notice this. This is very important. The negative sign here indicates the direction. So we're moving in the negative direction. If we wanted to turn this into a drawing on a number line, we're not given any information about where we start on the number line. It doesn't really matter in terms of position. We haven't talked about that today. But what we are seeing is something like this, where because we have that negative sign on the velocity vector, and typically negative is to the left and positive is to the right in terms of direction, then what's happening here is, well, we start really fast at a clock reading of 0 seconds, and then we've now slowed down. And our speed's about half, so I'll draw an arrow about half as large. And now our clock reads 4 seconds at that moment in time. So that's physically what has happened. We have gone, or we've moved to the left, and we're indicating how we're slowing down with these little velocity vectors that I've drawn quickly. All right, now let's move forwards and think graphically. And we're going to build up even more understanding of what's going on here. And ultimately, that's going to lead us to a concept that has the word associated with it called acceleration. However, right now, I do not want you to use this word at all. Kind of banning the word acceleration. Instead, I want you to think about three things. Is an object speeding up? Is an object slowing down? And what direction is the object moving in at any given moment in time? Remember, we're on a number line, and we can go to the left or we can go to the right. And if we're traveling to the right, we're moving in the positive direction. And if we're traveling to the left, we're moving in the negative direction. Okay, so speeding up, slowing down, and what direction we're moving in. Those are the three main ideas you want to be thinking about that ultimately will culminate in understanding really what acceleration is all about. Pause this video, look at the graph right here, and decide, is this object speeding up or slowing down? Go ahead. All right, well, hopefully you got it. And the right answer here is that the object is speeding up. Remember, we're looking at a velocity versus time graph, not a position graph. So reflect to see if you've misinterpreted what you were looking at up here, which is a common mistake. And if you thought this was a position graph instead of velocity, you would have thought this object was traveling at a constant velocity. But this is a velocity graph. So on this axis, we're seeing values for velocity, like 2 meters per second, 4 meters per second, 6 meters per second as time goes by. Okay, so you can hopefully clearly see that if we pick out a spot there on the graph, maybe that's 3 seconds or something, and then we come over here and we read off what our velocity is, we can see it's around 8 meters per second at that moment in time. And we reasoned that we started at 0 meters per second, so clearly we have sped up here. Another thing I want you to watch out for is don't think that just because we have a line that kind of looks like it's going up or something, and the word up here is occurring as well, that doesn't necessarily mean it's speeding up. We need to conceptually think through the graph. So I'm going to test your understanding for that now with the next question and see if you can get this one right. All right, so here's the graph. Inspect the graph and maybe think how it's different than the graph up here and decide, is this object speeding up or slowing down? Pause the video and really think about this one. This is an excellent question to start to build up this deep conceptual understanding of really what's going on when we talk about speeding up, slowing down, and things that accelerate. All right, so go ahead, pause the video and try this. Okay, well, here's the answer. This object is slowing down. Why? Well, I've helped you out and I've drawn some kind of tick marks here on the horizontal and vertical axes. Remember, this is a velocity graph, and the sign of the velocity matters. It has a meaning. It tells us what direction our object is moving in, right? So why don't you maybe think about how this can help us understand why it is slowing down. And just to help you out a little bit more, I'll continue the pattern of numbers here. -8, -6, and -4, -2, and then 0. 0 what? Well, these are all in units of meters per second. Okay. Sorry, this is looking a little weird. Looks like the number 20, so let me move that. Sorry. Okay. And so you should be able to see as time goes by, if we read off our velocity here, it's -8. Now here, it's -6. So we've slowed down. Remember, it's the magnitude of the velocity, the number, just the number, not the sign, that tells us how fast we're going. So we must have slowed down, and our speedometer would have read 10, 8, 6, 4, 2, and then 0, and we would have come to a stop here. It's just that this negative sign, what does that mean? That has meaning of the direction we're traveling in. So we're moving in the negative direction. Running out of space here. So we're moving in the negative direction while slowing down. That's the interpretation now of this graph. All right, well, or hopefully you got that. If not, don't worry. It's a common mistake students make. They see this upward trending line and they think that has something to do with speeding up. Next question I want to pose for you is, what would the slope of this line be, right? So go ahead and pause the video and see if you can figure that out. And I'll put some numbers on here. Why don't we make this 4 seconds right at the end there. Go ahead and calculate the slope, see if you can get the units right, and then we'll interpret it. All right. All right, so here's the result for the slope value. And you can see we just do rise over run. It's no more complicated than what you've done hopefully a bunch of times in the math class. You just got to get the units right here. So the rise, we can see we got a final reading of velocity of 0 meters per second minus the initial reading of velocity of negative 10 meters per second. Watch out for that minus sign there. And then down here, we've got a final clock reading of 4 seconds and an initial clock reading of 0 seconds. So rise over run, you do the division, and you get positive 2.5 meters per second for every 1 second. I've gone ahead and done the same thing up here, and you get a slope value on this one of also a positive number. I meant to have these to be exactly the same, but they're a little bit off. Oh well, doesn't matter. The main idea is to see that they're both positive. Okay, so they both have a positive slope value. So now with that, I'm going to ask you a question. All right, here's the question. Does the sign of the slope alone tell you if the object speeds up or slows down? Use the evidence over here on the left-hand side to articulate your thinking. Pause the video and think about it. All right, hopefully you got it. And the answer is no. The sign alone does not tell you if the object speeds up or slows down. Here in the top case, we're speeding up. In the bottom case, we're slowing down. But in both cases, we have a positive slope value. The number here is plus 2.67 meters per second for every 1 second, and here it's plus 2.5 meters per second for every 1 second. So they both have positive slope values, but one is speeding up and one is slowing down. All right, well, we're building up to really understanding what acceleration is all about. We'll define it again towards the end. Let's practice one more thing. Similar graphs, I've just put some different numbers on here. And I'd like you to construct some equations now. One for this particular model for an object and another equation for this one here. So pause the video using the numbers in the data table. I've provided graphs for you to look at as well, and see if you can construct two equations that represent two separate objects. Try it. Okay, so let's take a look. I've provided some helpful numbers. Hopefully you saw that in the data table, to get to the next value for velocity after every 1 second elapses on the clock, we just add 5 meters per second. And that corresponds exactly with what the slope on these graphs would be. 5 meters per second for every 1 second. That's what we update our velocity by. Notice we're just adding. In both cases, we're numerically adding 5 meters per second every 1 second. However, in this top case, that has the effect of speeding us up 10, 15, 20, 25, 30. But in the bottom case, that has the effect of slowing us down. Negative 40 to 30, negative 35, negative 30, negative 25, our speedometer values are getting slower and slower. It's just that we're moving in the negative direction here. So interesting that this positive sign is having a different effect on how fast we're going. This positive sign in the slope value here has a different effect on if we're going to speed up or slow down. And now let's write that in here. So we would have plus 5 meters per second for every 1 second for both of these values out in front. And then we'll add in our initial velocities here. So we had an initial velocity of 10 meters per second there, and we had an initial velocity at a clock reading of 0 of negative 40. So we'll come and erase this positive sign, and we'll put a minus 40 meters per second. Now you can go ahead if you want and test and see that our models will work perfectly now, and they will predict any future velocities at any future clock reading. Okay, so what is really then this plus 5 meters per second for every 1 second? What's the significance of this number? Well, it's telling us how to update our velocity. So the velocity changes by 5 meters per second for every 1 second. And what do we call this in physics? Hopefully you're shouting this out right now. It's what is called the acceleration of the object. So both of these objects had the exact same value of acceleration. Think about that for a second. One of them was speeding up. The other one was slowing down. And they both had identical values and identical signs, plus signs, for their accelerations. So I hope to uncover a common thought that students have incorrectly, where when they see plus signs for acceleration, oh, the object's speeding up. It's got a positive acceleration, right? No, totally wrong. It turns out that you cannot just look at the sign of acceleration to know if you're speeding up or not, or slowing down. So not enough info. I'll just write that here. Not enough info with just the sign to tell if speeding up or slowing down. Okay, there's something else that we need to know. And if we know this other piece of information along with the sign of the acceleration, then we can determine if we're speeding up or slowing down here in one dimension. Pause the video and see if you can write down what is that other piece of information that needs to be known in order to know if we're speeding up or slowing down. Go ahead, pause and think. Hopefully you got it. And it turns out that if you have knowledge of the signs of both acceleration and velocity, then you can determine if an object speeds up or slows down. Now we've already done 2 out of the 4 possible cases. We have 2 parameters, instantaneous velocity and acceleration, and we just need to look at the 4 cases. So just quickly, the case for when acceleration was positive, like positive 5 meters per second for every 1 second, and the velocity started out as positive, well, we were speeding up in that case. So we'll write that here. Think about the next case. Well, our acceleration value was also positive, positive 5 meters per second for every 1 second, but we began with a negative velocity, like negative 40 in my previous example. Then it went to negative 35 and negative 30 and negative 25, etc. As time went by. And so in that case, we were slowing down. So those are the 2 cases we've already seen. And you don't really need to write out a table of numbers anymore once you get this main idea about having knowledge of the signs of both of these parameters. Why don't you try the last 2 cases? So we could have a positive velocity and a negative acceleration, and a negative velocity and a negative acceleration. Really pause, think. This is a great test of understanding to see if you're getting these ideas correct about really what's going on with this new thing called acceleration. All right, so in these final 2 cases, are we speeding up or are we slowing down? Pause, think, and do some physics. Okay, so here's the answer. When the velocity is positive and the acceleration is negative, we're slowing down. But when the acceleration is also negative, but we have a starting negative velocity, then we're speeding up. And I've given you 2 helpful data tables to see that again in a similar idea as the other 2. I've kind of now written everything out for all 4 cases, and you can see we're mathematically now subtracting 5 meters per second for every 1 second, or you can think of that as adding a negative 5 meters per second for every 1 second as time goes by to update our velocity values. And in this first case, that turns into slowing the thing down, and in the second case, that subtraction turns into speeding the thing up because we began with a negative velocity. And you keep going faster and faster in the negative direction there. So what is the general pattern then if you want to kind of consolidate the sign of velocity and acceleration? Take a look at all 4 of these and see if you can simplify this into just a simple pattern you can remember. That way you'll always know what you're doing when you're looking at a problem with different signs for velocity and acceleration. What do you notice with this pattern? Okay, here it is. When velocity and acceleration have the same sign, whether it's positive or negative, you're going to be speeding up. And when the velocity and acceleration have opposite signs or different signs, you're going to be slowing down. All right, let's kind of finalize these ideas by properly defining acceleration. And here's a simple way to put it. It's the rate at which the velocity of an object changes. Notice I'm saying the rate at which the velocity of an object changes. I'm not saying speed there, I'm saying velocity, which has a very specific meaning in physics. And we saw today that we added, for example, 5 meters per second for every 1 second. And in one case, that sped us up, and in another case, it slowed us down, right? So it's very important that you see that it's the rate at which the velocity of an object changes. Now the type of, or the variable that's used is a. okay, lowercase a. The unit is meter per second for every 1 second. I'm going to write that in another way in just a moment. And then the type of quantity is a vector quantity in physics. So it has a direction associated with it. Acceleration has a direction. We saw some examples on the last slide there where we might have had something like acceleration is plus 5 meters per second for every 1 second. We also saw minus 5 meters per second for every 1 second. I think I left the units off on my last slide for brevity there, but you can see that acceleration can both be positive and negative, and that has a meaning in physics. We'll talk more about that as our course unfolds. But today you saw a simple example of how the positive and negative signs are interacting with velocity to change it. Now, another way to write the units would be like this. You could come over here and just do the division, and it would be meters divided by seconds squared. However, I really caution you that in the beginning, when first learning this, I think this is really helpful. Meters per second for every 1 second. Writing it in this way really helps you see what's going on and how we're updating a velocity value. Now, ultimately, when you kind of master that, you'll just abstract that away to meters per second squared is how that's often said. Meters per second squared. But that's a very abstract thing to say, and you really need to understand what it means. Meters per second squared. I don't understand personally what it means to square seconds, right? That doesn't have any meaning to me. I can understand maybe squaring meters. That's like area or something, meters squared or feet squared, right? But the squaring of time is way more abstract. So to see what it means, back out to these units that we're seeing right here. Meters per second for every 1 second. And then the formula, of course, that kind of ties it all together with the math is right here, where we can predict a final velocity value if we're given information about some initial velocity value, and we know our acceleration and then the amount of time that has elapsed. And then typically we often like to set our initial clock reading to 0 seconds, so this formula can also be written in the way I prefer it, usually like this. So we're plugging in a final clock value, or final clock reading, and we're being able to predict a final velocity value. Let's see another insight. Do some algebra. Take a look at our fundamental equation here that relates velocity, acceleration, and time interval, and solve for acceleration and see what happens. See what insights you can derive by just taking some simple mathematical steps that you already know how to do. Try it. All right, well, here's hopefully what you did. You solve for A, and you got the final velocity minus the initial. You consolidated that. That's just the change in velocity, a subtraction problem. And then we get the change in velocity over the change in time. I wonder what that is. Well, we go back to our graphical thinking, and we see that it's just rise over run. Here's our change in velocity for 2 particular moments that I picked out, and here's our change in time. And finding the slope of that line is just delta v over delta t. And that connects now visually how the meaning of the slope of our velocity time graph from before is showing up in the equation version. We're just looking at the equation of a line here, essentially, a good old y equals mx plus b, and now we're showing how the rise over run calculation is manifesting. So there you go. Here's a final test of understanding, taking everything we've learned in this video and seeing if you can apply it. Here's a graph, velocity versus time. It's a graph that looks a little bit different than any graphs we've seen. And your task here is to describe in words what this object is doing as it travels in one dimension. And before you attempt that, I've kind of broken the graph up into a few regions here, a couple regions. Region 1, which would be kind of this first segment. Then region 2 is this next segment, and I've also articulated this point right here, point P, which is where the graph intersects the horizontal axis right there. And I'm going to constrain you to not use the word acceleration at all in your explanation in words. You absolutely cannot use the word acceleration. This is going to force you to really think about the concepts that we've learned here today in this video. Okay. Also over here on the right, I have a little number line that might be helpful for you to kind of visualize the object moving in one dimension. I'm not even going to label the number line with positions. It's not important. All we know is that the object starts at some initial position, and to the right is the positive direction, and to the left is the negative direction. So go ahead and pause the video and see if you can write out in a nice few sentences exactly what this object is doing in terms of its motion. Pause the video and do some physics here. All right, well, here's the response that hopefully you were able to get to. The object is moving in the positive direction while slowing down. It stops for an instant and then speeds up while moving in the negative direction. Remember, it's the sign of the velocity that tells us what direction we're traveling in. So up here, those are positive velocities. We have to be moving in the positive direction if our velocity is positive. And then down here, we have negative velocities. We have to be moving in the negative direction if we have a negative value for velocity. That's a key idea that you understand. The sign of velocity always tells you what direction you're traveling in at any particular moment in time. So if you had something like this, you know for a fact, I'll even write that here, fact, the object moves in the positive direction. That's unlike the sign of acceleration, where if you just know the sign of acceleration, you don't know much. But with velocity, if you know the sign of velocity, you know exactly what direction you're moving in any particular moment in time. Cool. Now, I did put a value on here for the slope. I'm just giving you some number, -5 meters per second squared. You can tell it's a negatively sloping line here. And I'm doing that because I've got an important question for you about point P on the graph. So just investigate that point for a second, and we'll do the easy question first. At point P, what's the velocity equal to at that point? Just pause for 3 seconds. It's pretty easy. Okay, hopefully you got it. And you should see that right at that moment in time at point P, the velocity is 0 meters per second. My next question is a little more subtle and more important, and it's what about the acceleration at point P? What is the value of the acceleration at point P? Go ahead, pause the video and see if you can think about this. Is it still -5 meters per second squared? Is it now 0 meters per second squared? Is it some other value? Think about it, and then you'll see and get some feedback. All right, well, hopefully you got it. And the answer here is it's still -5 meters per second squared. If you zoom in on the graph and you look right here, you can see there's still a slope there. So if you were to do the calculation, you would get -5 meters per second squared at any point along this downward sloping line. And that really gets to the heart of what a rate of change is mathematically. Notice at this particular moment in time, we have a velocity value of 0 meters per second, which means at that moment in time, the object, if you were to look at the speedometer, it would say 0 on it, right, at that particular moment. But the rate at which the velocity is changing, so how will we update it for the future, right, it's still changing at a rate of -5 meters per second squared. So there's a difference between what the value of some quantity is at some moment in time, right here, this instantaneous value, versus how that will be changed as we allow the clock to run forward, say, a second. And in this case, what this is saying is -5 meters per second for every 1 second. So if we allow time to increase by another second, we will then need to update our velocity by subtracting 5 meters per second from whatever value it is. That would take us from this value of 0 meters per second and turn this into -5 meters per second after we allow time to elapse for another second, and then -10 meters per second, and -15, etc., etc., etc. So hopefully you can distinguish there between the value of the velocity at some moment in time here versus how that is changing, which is what a rate of change is all about, and that's what acceleration gives us. The key takeaways today were we used data tables, we used graphs, we saw how to construct equations, all relating to how we can speed up or slow down, how our velocity can change. We defined acceleration. We learned how the sign of just the acceleration alone is meaningless. We also have to have the sign of velocity to know if we're speeding up or slowing down. And we learned that describing motion in terms of the velocity, it's important to talk about, are we speeding up, slowing down, and what direction that we're traveling in. All three of these things ended up in our description in words of this of the graph. I think we had a different graph than this one, but of a velocity versus time graph. We could also talk about the picture of the system and physically see what the object is doing in that last graph that we had. In fact, I'll just redraw this to make it the same graph that we just saw. So this graph here, we were moving in the positive direction while slowing down. So you would have seen something like this. It's going fast, but it's slowing down. Then it stops for an instant, and now it moves in the negative direction and speeds up. That's what it's doing. One more time, it's moving really fast in the positive direction, but it slows down, stops for an instant, and then starts speeding up and moves in the negative direction. That's kind of the final piece of the puzzle, is for you to be able to take all of these abstract ideas and then see what the object is doing in the real world. All right, there it is. We really defined acceleration and everything about speeding up and slowing down in one dimension. We'll see you in the next video.